Welcome back to the Fik3505 Wireless Multiple Access Protocols course. In this seminar we will cover carrier sense multiple access protocols. The textbook references for this lecture will be ROM and CD Chapter 4 on CSMA protocols, and it could also be useful to look up the busy idle period analysis in the Client Rock Queuing Systems Volume 1 Chapter 5. Similar to the ALOA protocols, the CSMA protocols are found in the lower left corner of the classification of multiple access protocols. We will deal with probabilistic contention resolution. A main drawback of ALOA protocols is the way how collisions waste the channel resources. If two stations decide to transmit, they will keep on transmitting the whole packet even though there's a collision ongoing. If we could detect there was a collision ongoing, we could stop transmitting and free the channel for other packets to be successfully transmitted. This is exactly how human communication works. If two persons have a conversation, they listen before they talk, at least polite people do, and so if they detect that the other person is speaking, they will refrain from speaking. In this way, it's easy to schedule the speaking sessions between the two users. So can we mimic this in a protocol? Yes, and this is exactly what carrier sensing multiple access protocols are about. They employ what we call a polite listen before talk strategy, and we can avoid collisions by sensing ongoing transmissions. They're basically ALOA-based strategies. If there eventually is a collision, we reschedule the transmission to a later item of time. We also, in many of the algorithms, we also postpone the renewed sensing a random time. The requirements for this to work is that the path delay is short. We need to immediately be able to detect that the other guy is transmitting. And we need a fast receive transmit turnaround time. So when we sense the channel, it shouldn't take too long for us to get a signal in the air. Otherwise, somebody else could be sensing the channel at roughly the same time and find the channel empty, even though we already decided to start transmitting. If we could actually listen while talking, so-called collision detection, that would, we will see, will improve the performance significantly. So how does a carrier sense multiple access procedure work? Well, there are several steps. The first step is that we listen to the channel. Whenever we have a packet, we listen to the channel and to detect if there is an ongoing transmission. This is usually done by comparing the received power with some threshold, and if we are below that threshold, we assume that the channel is clear, and then we immediately switch to transmission mode and transmit our message. If this transmission is successful, we go into the idle mode and wait for the next packet. If the channel was found busy, we randomly reschedule the next sensing event, and the same thing we do if there's actually a collision. This random rescheduling of sensing events is usually called a non-persistent strategy. We'll come back to a persistent strategy when we hog the channel, wait until the transmission ends and immediately start to transmit our packet. But let's start with the non-persistent strategies. So how does this work, and how can there actually be a collision in a carrier sense multiple access system? Well, look at this timing diagram. We have two stations A and B, and let's look at the right-hand side, and we have introduced a couple of variables. Tau P is the propagation delay, the time it takes for a message to be transported from A to B, and TSW is the receives transmit switching delay, the time it takes from detecting the channel clear until we actually can bring power into the channel. And let's look at the right-hand side packet diagram, where we can see at this point channel is sensed by station B, and this is no ongoing transmission from station A, so B will find the channel clear and it will immediately begin its transmission sequence, and after a time TSW, at this point he will actually be able to bring a packet into the air. And after a time tau p, that packet will arrive at and it can be detected at station A. Now, if in the meantime station A in this period tau SW plus tau p after the first sensing also senses the channel, it will find the channel clear and will also start a transmission at this point, and we have a collision. The important time interval we have to look at is tau p plus tau SW. That is the time frame in which there can be multiple detections of a clear channel, and we call this the vulnerable period, and denote this by tau. To compute the throughput relationships, we look at the timing diagram, and we introduce two parameters. G is the sensing rate, and that is the amount of sensing attempts per time unit. This replaces the actual transmission events in an ALOA system. Here in a CSMA system, the sensing events follow this Poisson process, and we can use the same model as used in chapter 3. U tilde denotes the time spent for a successful transmission, and if we use the busy idle period analysis, we can compute the idle period duration, and we can find the expectation as 1 over G. The probability distribution can be simply found by the fact that I tilde will have an exponential distribution. And looking at the variable U tilde, that will be equal to T, that is the packet duration, if there is a successful transmission, and it will be 0 if there's an unsuccessful busy period. And we can compute the expectation of U, and that is simply T times the success probability, and the success probability is simply the probability there's no arrival in the vulnerable period or interval of length tau, in which we can see in the equation at the bottom. So let's look at how we can compute the expectation of the busy period. And we will be particularly interested in the busy period when there's a collision, as illustrated in the examples. Here we have a collision with 3 packets colliding, and we will in particular interested in the random variable y tilde, which is the arrival delay of the last packet in a collision. So in this example, y tilde will be, or t plus y tilde will be the arrival time of the last sensing point for the third packet in the example here. And then we can compute the length of the busy period, in this case when there's a collision, as t plus tau plus y tilde. The probability distribution of y tilde is simple to compute, since we know that since the packet we are interested in is the last packet arriving during the vulnerable period, it must be an exponentially distributed variable over the interval tau minus y. So the probability there will be no arrival in this period is simply e to the t minus y times a g. And using that, we can now compute the expectation of y, and we can there also using this equation we can finally get the expectation of y for this expression. And as in the ALOA analysis, we can now compute the throughput relationship as the relationship between the time spent for successful transmission divided by the total cycle time, so u divided by b plus I. And this gives us this equation. We have here introduced the normalized propagation time, which is tau divided normalized to the packet size. So this brings us to our first quiz. What happens in a non-persistent CSMA system as the normalized propagation delay or the propagation delay tau they go to 0? So for this case, derive the throughput sensing rate equation. And as usually, you can pause the recording at this time, figure out the answer, and restart the recording when you're done. And this gives us the solution. This is the expression for the throughput sensing rate relationship. Cap G is as usually the normalized sensing rate normalized to the packet size or packet duration t, cap t. So if we let a go to 0, e to the minus a g goes to 1. And a goes to 0, so we get the expression g divided by g plus 1. And we can realize that if we let g go to infinity, the maximum throughput actually goes to 1. The throughput sensing rate relationship, SG relationship, is illustrated in this diagram that shows the SG relationship for different normalized propagation delays A. As in the quiz 1, we can see that if A goes to 0, we can approach 1. The maximum throughput approaches 1, and this corresponds to a case there is no collisions. All collisions can be perfectly detected, and the channel will be filled with packets without collisions, so that's the ideal situation. We can also see that for large A's, when the propagation delay is very large, then the sensing is basically meaningless because it tells us very little what goes on with this large delay. And this means that the performance will approach that of non-slotted ALOA. The same way as the ALOA systems, you can see this clear bistable behavior that for every throughput or every input traffic rate there are two sensing rates, one corresponding to a low equilibrium where in principle the channel is always found clear, and a situation in other equilibrium point where the channel is most of the time found busy and very many sensing attempts are done. To illustrate this, we have quiz number 2. Let's assume that we have an infinite population non-persistent CSMA system, and that the expected delay parameter A is equal to 1/100th. And for a throughput of 0.3 arrivals per slot, compute the sensing rate, the probability of having a collision, and the expected duration of the idle period. As usual, you pause the recording at this point and do the calculations, and when you're done, you restart the recording to get the answer. And here are the answers. we start by solving the throughput sensing rate equation for lambda equal 0.3. We do this numerically. It's a non-linear equation, and we get the two equilibrium points. One is G equal to 0.61 and one is 785, and the interpretation is that in the low equilibrium point there are 0.6 sensing attempts, so that roughly 2 sensing attempts per packet that are done in the low equilibrium case, where there are 785 attempts done in the high equilibrium case. We compute the probability of collision, that is 1 minus the probability of a successful transmission, and the probability of successful transmission was that there was no other packet sensing going on in the vulnerable period, and that is simply e to the minus 0.01 g. And we find the answers to be 0.006 for the good or low equilibrium case, and very close to 1 in the high equilibrium case. So the probability of actually having a collision in the low equilibrium case is very, very small. And finally, we can also compute the length of the idle period, which is simply 1 over g. And the solution is then 1.6 packet intervals is the typical length of an idle period in the good equilibrium, and 0.001 in the bad equilibrium. In the bad equilibrium, packets are simply stacked on top of each other, so many transmission attempts there are. One can of course wonder, why should we treat a sensing the channel busy as a collision in the ALOA protocol and then randomly delay our resensing of the channel? Of course, what one could do is to wait until the sense transmission ends, and then immediately when the transmission is over we can start our own transmission. And that is called the persistent CSMA protocol, and the timing is illustrated in the diagram here. At this point we have a transmission started. There is a packet that finds the channel idle and starts transmitting. And during the transmission of this packet, the white packet here, another packet or another 2 packets are sensing the channel, and both of these stations wait until the end of the transmission, and at roughly this point they both start transmitting their packets, and we have a collision in this interval. During this collision interval there is one more packet arriving, and that will then be transmitted immediately when the channel becomes idle. Then the channel becomes idle again, and we have another transmission starting in this interval. We distinguish between 2 types of transmission intervals. One transmission interval we call type 1. Those are those intervals that will begin with the transmission of 1 packet, and we can see that the first, third and fourth transmission period they are of type 1, whereas the second transmission period is of type 2. In this transmission period there are more than 1 packet waiting for being transmitted immediately when the transmission of the first packet ends. So what we can do to analyze this is that we describe the model by using a state model, and we see that the system moves between 3 types of states. It's a transmission period of type 1, transmission period of type 2, and the idle period, or the 0 in this case. And using the this state diagram, we can compute the transition probabilities, and then we can compute the conditional lengths of the busy period for the different states, and finally we can get a similar relationship, a quite complex relationship between S and G. Interesting to see is as A goes to 0, the maximum throughput doesn't approach 1. And this is also illustrated in the next slide that shows the throughput relationship. Here we have the throughput sensing rate relationship for the one persistent CSMA, and you can see that the maximum throughput doesn't go to 1, even though A goes to 0. ROM and CD also considers slotted CSMA. Here we assume that all the transmission or the sensing attempts have to take place in a slotted system on a time synchronized way, and we assume that we use a mini slotted system that is uses slots of size equal to the maximum propagation delay in the system. And using this we can find that the throughput for a slotted system is slightly higher than for a non-slotted system, but it's only marginal. So far, our carrier sensing technique has helped us to avoid collisions, but when collisions occur, they still make the same damage as in the LOA system. So the question, can we detect that a collision is ongoing? And if we can detect this early, then we could terminate the transmission and to avoid the waste of channel resources and free the channel for other transmissions. And to do this properly, it requires that we can listen while talking. And how could this work? In cable-based systems like the 802.3 Ethernet standard, stations are connected to a coaxial cable or connected through twisted pairs. And each station has a transmitter connection and a receiver connection to the common cable or the common bus. And when a station transmits, it is able to compare the transmitted signal, the red TX signal, with the green RX signal. And if the signals are sufficiently equal, then we assume that there is no collision and we can keep transmitting. But when there's a significant difference between the transmitted and received signal, then we know there's a collision going on, and in order to make sure that everyone in the system knows that the packet has been colliding, the transmitter sends a jamming signals, alternating ones and zeros over the channel, also sometimes called the consensus reinforcement signal, to ensure that all the terminals are aware of the collision. So let's look at the collision detection timing and see how much time we have to spend until we have detected the collision and can cease transmitting, and thus freeing the channel for other transmissions. Again, we have a timing diagram with station A and B, and we assume that A starts the transmission here at T0, and that B starts the transmission here at T1. At this point, station A will realize that station B has started a transmission at the same time, so A becomes aware of the collision, and A will now, and this will be a time interval tau CD, the time spent for carrier detection after the packet physically arrives at A. At this point, A will start the jamming signal or the contention reinforcement signal to make B also aware that there's a collision going on. And at this point of time, B will stop transmitting its contention collision reinforcement signal, and at this point A will stop transmitting, and this point B will stop transmitting and be aware of that a packet has been detected. So the total time spent for an unsuccessful transmission will be gamma, which is 2 tau plus tau CD plus tau CR. And using this we can compute the SG relationship, which is somewhat complex. We have introduced gamma prime as the normalized gamma to the transmission time of a packet. So this is the performance of the CSMAC system, and again, as A goes to 0, we get perfect collision detection and perfect avoidance of collisions, and we get a throughput that approaches 1. But we can see that for A equal to 0.1, the maximum throughput will be very high by keeping the collision intervals very short. Again, as A becomes large, the sensing of collisions will have a limited value, but we still make use of the short collision intervals due to detection of collisions. So the performance now will be slightly higher than the one for non-slotted ALOA. And finally, if we compare all our CSMA schemes, we get the following graph. We can see that the non-persistent CSMA with collision detection, of course, gives the highest performance. Also, the one persistent scheme with collision detection has good performance. It's also interesting to see here that the one persistent CSMA has better performance than the non-persistent CSMA for low traffic loads. And of course the reason is that if there's low traffic, then it is no use of delaying resensing very long, and instead we can wait for the end of the transmission and immediately transmit our packet. So if the throughput rate is small, then the probability that there will be more than one packet waiting for transmission is very low. But we can also see how the one persistent CSMA performance drops off very rapidly, and the maximum throughput is significantly lower for the one persistent scheme. So this brings us to quiz number 3, and you have to review the following 4 statements and find out which are true. More than one statement can be true. And as usual, you pause the recording, figure out the correct answers, and restart the recording when you're done. So here are the correct answers. The maximum throughput of a CSMA system does not increase increasing the delay parameter. So remember that if A is increased to large values, the performance of CSMA will approach that of non-slotted ALOA. The maximum throughput of a non-persistent CSMA system approaches unity as A goes to 0. That is true. CSMA with collision detection will outperform non-persistent CSMA except when A goes to 0. Yes, that is also correct. When both schemes have an A with going to 0, the maximum throughput will be 1 for both. And one persistent CSMA outperforms non-persistent CSMA for low traffic loads. That is also correct. So how can we do collision detection in wireless systems? In practice, this turns out to be quite difficult. Simultaneous reception and transmission or full duplex radios are difficult to design since the large dynamic range. Particularly in outdoor wide area systems, the transmit powers are on the order of watts, whereas the receive powers are in the order of nanowatts or even picowatts. So it's very difficult to receive a signal at the same time that a transmitter is transmitting 1 watt on the same antenna. So the solution that has been proposed is to do something close to slotted CSMA, and that is we call collision avoidance. And the idea is to contend using mini slots in a preamble of a packet. And if a collision is detected, we do not send the rest of the packet. An example where this is used is IEEE 802.11 or the Wi-Fi protocols. To give you a basic idea what collision avoidance is about, we illustrated with a simple example. This will be treated in more detail in the next session, which is on IEEE 802.11 Wi-Fi protocols. The procedure is based on that we have a number of preamble mini slots, and they could be n mini slots. The size of the mini slots is about tau, the propagation delay or the maximum propagation delay, and then we have the data packet transmission. So how does it work? Every station that has something to transmit at the beginning of a preamble will pick a random number between 1 and n, and then it will start listening to the mini slots. And if it cannot detect any carrier in any of the mini slots until its own number comes up, it starts transmitting its packet. So in the example above here, the green station has picked number 2, and since slot number 1 was empty, it will immediately start transmitting its packet at mini slot 2. If a carrier happens to be detected before the station's number comes up, it waits until the end of the packet transmission, and then immediately a new preamble starts. So the typical CA schemes are persistent schemes, so they start transmitting immediately after the end of a previous transmission. Collision can still occur, of course, if 2 stations happen to pick the same random number, so then they will start transmitting at the same time. And in this case, we cannot prevent a full collision of the whole packet, since the transmitters and receivers cannot operate at the same time, so they cannot detect the collision when it's ongoing. A nice feature is that we can actually stabilize the system by adjusting n. And in 802.11 the popular exponential backoff is chosen. This means that whenever we actually have a collision, we see this as a sign of the many packets scheduled for transmission. So in that case, we double n in every interval when there is a collision. So if there are many collisions occurring, then the number of preamble slot increases, and thus the probability that 2 stations will pick the same number will decrease. So this brings us to the summary. CSMA protocols are listen before talk protocols. They avoid collisions by sensing ongoing transmissions. But in principle, they're still LoA-based strategies. But what we do is that we reduce the vulnerable window for collisions. In order for them to work, we need a short path delay. If the path delay becomes very long, the performance will drop basically to the LoA performance level. And we also need fast receive transmit turnaround times. The time between we have to sense the channel idle until we actually bring up our transmitter to full power should be short. If we can listen while talking, as we can do in wire-bound Ethernet systems, that will significantly improve the performance.